Okay, let's dive into this. Look, if you've been following the whole evolution of AI coding assistants, you've probably felt that lingering anxiety about handing over control, right? I mean, the idea of a black box AI just roaming freely through your code base, especially with access to production, honestly, it's the stuff of engineering nightmares. It's enough to make you want to revoke all your API keys just thinking about it. But in today's explainer, we're going to look at how Google's Antigravity CLI completely flips that script. We're going to visualize its execution lifecycle, not as some chaotic chatbot, but as a highly controlled mechanical reality. Think of it less like a chat window and more like a relentless autonomous factory floor, where literally every single action is strictly scrutinized. To really understand where we are right now, we have to look at where we've been. We are finally, thankfully, leaving behind the era of those first and second generation chatbots. Those tools were unbounded, they were chaotic, and let's face it, highly prone to hallucinating code that just didn't work in your specific environment. It just left you manually copying, pasting, and debugging all their mistakes. But now, we're entering the era of the third generation CLI harness. This new paradigm is deterministic, it's highly structured, and strictly policy-bound. Instead of just, chatting with an LLM, the anti-gravity CLI functions as a full-blown orchestration harness. It manages state, it handles file system access, controls subprocesses, and most importantly, it wraps all of that in strict, verifiable loops. So here is our factory map for this explainer. We'll start with the agentic conveyor belt. Then we'll inspect 3 physical checkpoints a task must pass: instructions loaded, pre-tool use, and post-tool use, before wrapping up with total organizational compliance. Section 1, the agentic conveyor belt. Orchestrating the AI runtime. Let's move to this and see how it builds, picturing our runtime as a continuous, relentless conveyor belt, carrying a single task. So the anti-gravity CLI runtime basically operates like this relentless conveyor belt. It's propelled by a foundational 4-step loop: observe, plan, act, and verify. Let's say you issue a command, like asking it to refactor an authentication module. Well, first it observes, assembling deep context from your directories and memory files. Next, it plans, generating structured artifacts like an implementation plan before it takes any destructive action. Then it acts by invoking native tools deterministically. And finally, it verifies. It validates those mutations by running test runners and linters, and crucially, feeding any errors right back into the context so it can self-heal. This continuous engine is exactly what propels the agent directly down the line toward our heavy security gates. There's a great quote here. The role of the developer is shifting from direct line-by-line code generation to intent definition, requiring strict deterministic circuit breakers. And that is so true. To thrive in this new paradigm, systems engineers can't just cross their fingers and hope that AI does the right thing. I mean, if an autonomous agent gets stuck in a loop trying to fix a broken test with bad logic, it could burn through tokens endlessly, or worse, completely mangle a repository. So we absolutely must rely on these exact deterministic circuit breakers to prevent infinite failure loops and strictly enforce our overarching architectural constraints. Section 2, Checkpoint 1, Instructions Loaded, Validating Blueprints. We have officially arrived at the first heavy metal blast door on our factory floor. Think of this instructions-loaded hook as an automated mechanical scanner positioned right at the factory entrance. It fires the absolute moment configuration rules are parsed, literally before a single line of code is actually executed. It's a real game changer because it allows your enterprise compliance tools to inject runtime policy assertions directly into the agent's brain. It ensures the AI explicitly knows the house rules before it even thinks about picking up a hammer. This scanner is exactly how you prevent rogue agents. By intervening this early, it reads overarching organizational rules from files like Gemini.md. It enforces structural architectural constraints, and it loads declarative security policies. Now, human engineers usually pick up these rules over, months of onboarding, but the AI, it needs them instantly. By front-loading these strict constraints, you guarantee that the AI shares the exact same operational picture and compliance boundaries as your most senior human engineers, right from the starting line. Section 3, Checkpoint 2, Pre-tool Use Barrier, the Protective Blast Door. We're continuing our momentum down the conveyor belt to our next physical intervention. So once the blueprint is approved by that first scanner, the agent formulates a plan and prepares to invoke a tool, like, say, running a bash script. But actually, right before that tool is invoked, it hits the pre-tool use hook. Picture this as a massive, heavy, physical steel barrier descending to intercept unsafe commands right before they hit the terminal. It's a blocking middleware hook acting as a strict security circuit breaker, and it evaluates the agent's exact intent against your project's absolute safety invariance. And this brilliantly illustrates exactly what we're protecting against. Imagine the absolute devastation of a hallucinated, unflagged database drop command hitting your terminal. Ouch, right? Well, the pre-tool use hook completely halts the conveyor belt if it detects that. It aggressively intercepts private token leaks before they are ever executed, totally preventing you from accidentally committing an AWS key. It dynamically denies access to protected directories like your migrations folder or highly sensitive files like your .env file. The agent might try to execute these based on a bad assumption, but this deterministic, programmatic wall simply will not let fatal errors pass. Section 4, Checkpoint 3. Post-tool use brush, the mechanical polisher. The code has survived the barrier, and now it arrives at the final stage to be cleaned. Okay, so the code survives the blast door, the tool executes, and the files are successfully written. But, our factory floor isn't quite done yet. Welcome to the post-tool use hook. If the previous hook was a heavy barrier, this one is a high-speed mechanical polishing brush. Firing immediately after tool execution completes, it doesn't just rely on the AI's language model to write perfectly clean code. Instead, it uses this programmatic hook to aggressively scrub and validate the raw output deterministically. Let's break down the mechanical steps of that brush in action. First, it runs deterministic auto-formatters. Think prettier for JavaScript or black for Python, instantly standardizing the syntax. Second, it immediately triggers test validation tools, like PyTest, directly on the freshly edited files. And only after the newly generated code is mathematically proven to pass its tests does it reach step 3, staging and committing to the Git workspace. Because of this mechanical brush, every single file leaves the factory floor spotless, perfectly formatted, and tested. Section 5, Total Organizational Compliance, Trust at Enterprise Scale. Let's zoom out from the individual checkpoints to view the overarching goal of this highly secure factory. Now, what's really interesting about this slide is how it all comes together. We have instructions loaded acting as the scanner to guarantee policies injected up front. We have pre-tool use acting as the barrier to guarantee hazards are strictly blocked from execution. And we have post-tool use acting as the brush to guarantee formatting and testing are relentlessly enforced. Layered together within the Antigravity SDK, these 3 distinct lifecycle hooks interlock to form this incredibly robust, impenetrable compliance shield around the entire AI runtime. The ultimate goal of these Python SDK hooks and deterministic circuit breakers is absolute precision, 100%. By actively moving compliance out of the LLM's inherently unpredictable prompt and directly into these programmatic lifecycle hooks, we guarantee 100% adherence to enterprise policies. The large language model can be as wildly creative and, let's be honest, stochastic as it wants while it iterates inside its isolated sandbox. But the factory floor's final output, it remains perfectly, reassuringly deterministic. Which brings us to arguably the most critical question facing every enterprise engineering team today. How do we actually trust autonomous agents at scale? I mean, if we just treat them like magical chatbots, we simply can't. But by replacing blind trust with these rigid, verifiable mechanical checkpoints, we shift our entire engineering culture from merely hoping for good code to structurally guaranteeing it. So the crucial point is this. The future of engineering isn't about typing syntax faster. It's about building smarter, safer factories. It's about clear intent articulation, meticulously defining architectural invariants, and deploying the exact circuit breakers we explore today. By mastering the Antigravity CLI lifecycle, you aren't just coding. You are securely orchestrating the next generation of software development. So I'll leave you with this. Are you still handcrafting code in an unpredictable sandbox? Or are you ready to build your own autonomous factory floor?